spherical coordinates. It looks, oh man, it looks quite horrible, but actually we're going to see it's not that bad. All right, let me get my stuff. I will begin with a word of prayer. Dear Father, we thank you for this day and for your many blessings. Just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So this is lecture 11, believe it or not. And basically today we're playing with Legendre polynomial potentials. All right. And so basically we're solving Laplace's equation in sphericals, where, that was supposed to be where, use your imagination, no phi dependence. All right, no phi dependence. I have a strong feeling that the issue of phi dependence is exactly the same question as what is to be continued in the cylindrical Laplacian that we started tinkering with last time, but we didn't get through. All right, so let me remind you what we got to. We figured out that our general solution looks something like this. V of r theta equals to the sum L equals 0 to infinity of a sub L, r to the power L, plus b sub L divided by r to the L plus 1. All of that times the Elf Legendre polynomial in cosine theta. All right? And for the sake of reference, let me rattle off a few of these, Legendre polynomials. I'll put them over here. So like P0 of x equals to 1, P1 of x equals to x, P2 of x is equal to 1/2 of 3x squared minus 1, P3 of x is equal to 1/2 of 5x cubed minus 3x. You notice these are really kind of interesting formulas. You notice that like the odd ones only have odd powers and the even ones only have even powers. See that? That's kind of cool. Now, as I mentioned, I have a derivation of these a la doing the problem that's in Griffiths. If you look at my posted solutions from my undergraduate days. So we will leave that suffering in my youth and be content to write these from a table in here. You know, I'm not sure we're going to need all these. I'm just putting them up here for the sake of context, you know. In fact, this is entirely too much for this lecture, but there it is. Here's the first 5 Legendre polynomials. Now, much like sine and cosine, like sine is orthogonal to sine with respect to integration, and cosine and sine are in some sense orthogonal. It's, with respect to particular integration, if you integrate products of sines or products of cosines, or a mix of in between, you'll get 0, right? So this gives rise to like the arithmetic of the Fourier series. Basically, if you multiply your expression by a sine or a cosine, you're able to make a whole infinite series collapse to just one term. All right, but we don't have an infinite sum of sines or cosines here, right? We have an infinite sum of Legendre polynomials. But these are, again, part of a larger discussion of what are called orthogonal polynomials. And every orthogonal polynomial actually, well, they don't necessarily come with the same inner products. Like sometimes you have to multiply the orthogonal polynomials by some other function in order to kind of get the sort of dot productness, if you will. And in this particular context, the theorem that we need, where the magic happens, is simply this. Don't worry, I'm not going to prove it. I'm just going to claim it. Integral from 0 to pi. I'm not going to name it, though. I'm just going to claim it. Sorry, that's a dated reference to a forgotten heresy. Let's see here. Cosine theta, PL, PK, sine theta, d theta. Actually, I don't like this k. I'm going to make it an m. It's easier to read an m. LM. There we go. And that is going to be equal to 2 over 2L plus 1 times z Kronecker delta of L comma m. So this right here, this is the secret sauce to actually calculate formulas for the coefficients of this problem. And so we can use this theorem to solve for the coefficients a sub L or b sub L in applications. All right? So like let's get into it. So the first example will just be, we're going to specify a potential on a sphere, and that potential will only depend on the polar angle, the angle off the z-axis, the theta. All right? So example 1, we're going to suppose, did I remove? Oh, you did move the camera. Suppose v, of r comma theta is equal to v sub naught of theta. All right, so this is, we're specifying values for potential on r equals to r, and we want to find v within this hollow sphere. So let me kind of draw a picture. What's going on here? We have, like so we're given v naught of theta out here, right? It's specified all the way around, right? And we want to find v up in here, all right? So we want to look at r less than big R, all right? And we're given that the voltage, the potential, only depends on theta. So it's manifestly independent of the phi angle. All right, so we've got this general template solution over here. How does it go? Let's think about this. We're looking in the region where r could be 0, right? So what do we not want to use there because it would be unphysical? What goes to infinity if you put r equal to 0? This one or that one?
The second.
Yeah, this is bad, right? That blows up at the origin, so this is not part of the solution. So we simply set all the b's to 0, and all that leaves us is this guy. So already our solution is only half as complicated as it was. All right, so we've got, I regret drawing this picture right in the middle of everything. That was dumb. Permission to move picture up to here. There we go. All right. Yeah, I wasn't really asking. But Sorry. Anyway, all right, so we got V of r theta is equal to the sum L equals 0 to infinity of a sub L, r to the L, and then times this monstrous p sub L of cosine theta. All right. Which is kind of scary because it's the unknown, isn't it? I mean, I gave you the first 5 over there. No charge. I mean, they're also in Griffiths, so don't thank me too much, but... Yes. Okay, so that's that, right? Now, we know that V sub naught of theta has to be equal to, then, the sum L equals 0 to infinity of a sub L, little r replaced with big R to the L, p sub L cosine theta. This is the boundary condition, right? We're fixing the voltage on the edge. Now we use the theorem. And I won't do this, like we don't actually need to do this so much, but I think I need to go through this calculation with you just to be sure we understand everything. But like, so what we're going to do is we're going to take this, multiply both sides by this gadget right here. All right, so I'll do that. So we've got, and we're integrating from 0 to pi. Integrate from 0 to pi, the given voltage, the boundary voltage, Pm of cos theta sine theta d theta, and that's equal to the integral from 0 to pi of this summation L equals 0 to infinity of a sub L r to the L p sub L of cosine theta times Pm cos theta sine theta d theta. All right, you see what I did? I took my boundary condition and I just multiplied by the mth Legendre polynomial and sine theta, and then I integrated that from 0 to pi. And the reason I did that was simply so that we can play the usual game, which is to bring the integration inside the summation, you see? So we take, oh, okay, well that's really the sum L equals 0 to infinity, a sub L r to the L. And then we've got this integration from 0 to pi of PL cosine theta, PM cos theta, sine theta, d theta. All right. Now Griffith, by the way, Griffiths does explain a little bit more about this in the book if you look, but I don't think that really helps us solve problems even a little bit, so I haven't included it in the lecture. All right. Griffiths does have a little bit more background on like the origin story of the Legendre. You can look at it. I just don't think it's physics, honestly. So it's funny, come from me. But this, it turns out, is sum L equals 0 to infinity of a sub L r to the power L, and this picks up a 2 over 2L plus 1 the Kronecker delta L comma M. But the Kronecker delta is the natural enemy of the infinite sum, right? And as such, we're just left with a sub m r to the power m times 2 divided by 2m plus 1. And so, we get, a sub m is equal to, solve for it, Actually, let me not solve for it here. I'll regret that. I'm going to solve for it over here and put it in the corner. We're not really going to use it, so I should put it over here in the corner. So if we solve this for AM, it gives us AM equals to, multiply, we've got a 2m plus 1 divided by twice r to the power m, integrate from 0 to pi, the given voltage, theta, PM, cosine theta, sine theta, d theta. There you go, stick a fork in it, we're done. Because all we have to do is do this integral, all right, and then plug those numbers, whatever they are, back up in here, right? Of course you need to change to m, you know. If you'd like, I can change this to L. When we change it to L, watch. You guys watching? L, 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 there we go. Now you just stick it up in there after you do these integrals for your given voltage, and you've solved the problem. But the cool thing is we don't actually have to solve problems like that. There's tons of problems we can solve without actually doing this, all right? So I want to show you that. So like example 2, which is actually a follow-up to example 1, we have, well, I'm sorry, this is still example 1, my bad. Example 1, continued. This time we're going to let v theta be given. And we're going to follow Griffiths, and I like Griffith. I think this is a great example, actually, so I think I'm like sticking with it. He's like, well, what if the voltage is k times sine squared theta over 2? Right? Just to kind of give you a more concrete example. Suppose that is the voltage that you've pasted over the sphere. So we can use trigonometry and rewrite the given voltage as what? Like k over 2, right? 1 minus the cosine of theta. You guys with me? So you guys rewrite those as Legendre polynomials. While I'm checking the camera, you figure it out. Rewrite those as Legendre polynomials. We only need to use like P0 and P1. Remember what? I'll write them down here on this board again. So what was the deal? P0 of x is equal to 1. P1 of x is equal to x. Those are easy enough to think in, aren't they? So this is literally k over 2. Let me write it down here. It's k over 2 times like P0 of cosine theta minus P1 of cosine theta, which, let me write this again. This is k over 2 P naught cos theta minus k over 2 P1 cos theta. Now why am I doing that? The Legendre polynomials are independent functions. So if you have two expansions of them, you can compare and equate coefficients. That's how this works. I mean, okay, if you want me to be more like, if you want to just calculate it, we can use this theorem. All right? We can use the purple theorem. We can multiply this by, you know, other Legendre polynomial sine theta, integrate from 0 to pi. And we can do the same thing to this, and we can end up proving that the only way that you have equality is if all the a sub l's are 0 except for 2 of them. See, this, let me get some color coding here. This guy has to match up here, right? So comparing, what can you see? What's like a sub 0 is equal to what? So we see a sub 0 times r to the 0 has to be equal to k over 2. Because that's the zeroth. The first one, a sub 1 times r to the 1 minus k over 2. Lo and behold, we have found that a sub 0 is k over 2, and a sub 1 is minus k divided by 2r. Let me put it all together now. So hence, we have v of r theta is, a0, r to the 0, p sub 0 cosine theta. I'm just writing out real dumb, all right? Plus a1, r to the 1, p1 cosine theta, all right? But because of the work we just did, what is that equal to?
K over 2 r0 minus n.
Oh yeah, k over 2. Of course, r to the 0 is just 1, right? So so it's just k over 2. And then over here is minus k over 2r times r, right? And p1, that's just cosine theta. So to clean things up a bit, we just have k over 2 times 1 minus r over r cos theta, I believe. And there you go. That's the voltage within the hollow sphere that satisfies this surface voltage. Now, the scary part of this calculation is seeing how to manipulate a given trigonometric expression into a linear combination of those powers of cosine. Like if I put a cosine cubed here, could you play a game where you be glad I haven't made your wait a minute, haven't made the homework yet for you guys? Maybe. I mean, if I gave you the given voltage was cosine cubed, right? You'd have to somehow find a way to like solve for the cube in terms of the. But I think you could play games with this. Like if you isolate the cube, then you've got like p3 minus like 3/2 x, and then you can turn the x into a p1. I think actually it may not be that bad. Maybe it's not as bad as I think it is actually. I guess I can just make it homework to see how bad it is. But of course the bad thing about that is that I do actually solve the homework too, so it does come at a cost to me. Yeah. Speaking of that, I'm working on the solution to mission 2. I have most of it solved already. I just didn't solve the last 2 problems, and I kind of want to solve them before I post it because otherwise it's kind of lame. So I'm trying not to be lame. Example 2. Same song and dance, but this time we want to find the potential outside of the sphere. All right? Example 2. So we still have, V naught of theta is equal to V of R theta, but now solve for R greater than R. So basically, what happens outside of the sphere, right? So this time, you guys get me started. We do V of R theta equal to what? The sum L equals 0 to infinity of, all right, so here we have little r going to infinity in this case, right? So if we want a physically reasonable voltage function, potential function, I need to remove the A sub L terms this time. All right. Well, we can, in principle, maybe you should leave the constant one because that's not problem, right? But since this is localized, we're free to make the constant 0. So without loss of generality, except perhaps the choice of potential, I think we're forcing the voltage to be 0 by making the choice A sub 0 equal to 0. all we need is the b sub L divided by r to the L plus 1, right? And of course, your handy dandy p sub L cosine theta, that's the potential, all right, in this context. And then what do I want? I want V of big R theta equal to V sub naught theta, the given voltage, and that's going to be equal to the sum L equals 0 to infinity, B sub L over big R to the L plus 1 times the Legendre polynomial of order L evaluated at cosine theta. Now I want to solve for B sub L. I will not subject you to writing that all out again. I'm just going to write down the answer because it's obvious what goes on. What we do is we multiply both sides by p sub m cosine theta times sine theta, integrate from 0 to pi, use the purple theorem, solve for the B sub L. Same trick again. And what it works out to is that B sub L actually works out to 2L plus 1 divided by 2 times r to the power L plus 1. Integrate from 0 to pi your given voltage at theta times the Legendre polynomial at cosine theta. I have trouble drawing that. Cosine theta times sine of theta, d theta. There you go. Do this integral, plug those numbers in there. We're done. You solved it. Now, of course, again, I don't actually want to do those integrals, right? If it's actually a problem I give you guys, I will do some kind of, hokey pokey thing where I give you the v theta, which is either directly a Legendre polynomial in theta, or a little bit of trigonometry gets you there. And then you just do the matching like we just did in the follow-up to example 1 again. All right? I'll try to add something like that to the notes when I finish writing them up. I just don't have it ready yet, and I think we should go on. So the next example, a little bit more interesting. Suppose we have the electric field is equal to E naught Z hat most places. Then we put, conducting sphere in this otherwise uniform field. What we want to do then is to find the voltage. Let me try to hazard a picture here. So here's the deal. Like, this is the sphere. We'll put it at the origin because why not? So radius r as usual. And so the electric field lines, they're vertical. So we'll make z go up. Okay. So like the field lines out here, they're just if they're a little bit away from the sphere, nothing's happening. But if we're close to the sphere, what can the field lines go through? What do they have to do? They have to, do you guys remember from like physics 232? What do the field lines do? They'll bend around, right? They have to bend around. So it's got to do something like that. I don't, that's probably too extreme, but something like that, right? And why does that happen? Because where does the positive charge get pushed to? Where does the positive charge go? In the direction of the electric field or opposite? In the direction, right? So positive charges get pushed up here, and the negative charges get sucked down there. Of course, in practice, there's just one or the other, right? You don't really find positive and negative flowing charges in a metal, right? That would be problematic for other reasons, like what happens when those meet inside the metal. Yeah, when like positive and negative charges meet, it's not, there's energy. It wouldn't be stable. Like it wouldn't, So the real thing is that there's electrons that are moving, and the positive charge is actually the absence of electrons. It's holes that we count as positive, you know? But anyway, enough of that. That was physics, wasn't it? That was physics. This is a physics course. I probably should talk more about that kind of thing. But anyway, my apologies. Hey, this course will be taught by an honest-to-goodness physicist next year, probably. But so, listen. How do we find the voltage then on the sphere? See, it's got z is this. The z is this way, right? Like this is the z-axis, right? So like we can take this to be the x-axis, right? And the y-axis is coming out at you. This is the problem that has the right kind of symmetry for our general template. It's got no phi dependence. So we're well within our rights to hit this over the head with our general, you know, our general solution over there. So let's work on that. All right. So I guess so maybe something we should notice here is, I mean, I described the uniform electric field, right? We're trying to set up, you know, the voltage, the potential, right? So I need information about the potential. What does this tell me about the potential? Yeah, I guess my constant across the sphere. Yeah, that's an equal. That's right. So we can put v equals to 0 right here, right? Ground the sphere, right? Then, I mean, we can define that to be 0 voltage. Then that's going to put 0 voltage like that way, all the way out, right? But certainly we can't have 0 voltage up there or that way. So it's a kind of interesting problem that way. How about this? You can see that V has to be equal to minus E naught Z away from the sphere, right? Why is that? Because this formula gives you the gradient of V with a minus is equal to E naught Z hat, right? Let's put that in terms of sphericals, right? In other words, V of R theta should be equal to minus E naught R cosine theta for R much, much greater than R, right? That's a boundary condition for us. Does that make sense? I hope it makes sense. And so that's one thing we have. It has to be going to minus E naught R cosine theta for that. And we're also going to have that V of R comma theta equals to what? That was, I already talked about this choice a second ago, but let's write it down. Zero, right? We put the, you know, it's an equal potential, we made it 0. So we go back, yep.
So just to be clear, are we like imagining there's like a ground plane through the whole, like this?
No, it's a conducting sphere.
Yeah.
So that's all. It doesn't, my comment about this being 0 voltage all that way out,
Yeah.
doesn't really matter to our analysis here. I think it's true though, because the, because it's an orthogonal trajectory to the field lines by the symmetry going out, which means that you're not lowering or raising voltage, and if it's 0 volts here, it stays 0 volts. And the only place that I'd have that orthogonal trajectory comment is right at the equator of the sphere where it can go out.
I got you.
And I'm never leveling up equipotential-wise.
Except for everywhere else, where it's also 0 for the sphere.
Well, but they're the curving. All right. Good question. Something to think about, but I need to. I got more to do. Let me keep going. So, our general solution is still what it was, right? We're still, thinking about v of r theta equals to the sum L equals 1 to infinity of a sub L r to the L plus b sub L over r to the L plus 1 times yield Legendre polynomials of order L evaluated at cosine theta. Right? And I can't I can't just throw away the A's and the B's this time. All right? Because well, I mean, maybe I don't need to solve. First of all, I'm only solving it outside, right? Let's be clear. I'm solving it outside. Yeah? To be clear, the instructions here are find v of r theta for r greater than r. Why don't I have to find it for r less than r?
It's 0.
It's 0, right? It's a conducting sphere, so dumb. I mean, we got that. Now, the voltage has to be continuous, right? So, if we look at v of r theta, that has to be 0, but that also has to be, that implies that a sub L r to the L plus b sub L over r to the L plus 1 has to be equal to 0 for all L. Because the Legendre polynomials are independent, so their coefficients have to separately vanish in order to achieve the 0 voltage. I get one condition for every L. Which means that the A's and the B's are not disconnected, in fact. You see? My, whichever way I want to solve for, maybe the B's, B sub L is, like minus A sub L R to the L. Come on. I can't do math. Minus A sub L R to the power L times R to the L plus 1, right? So B sub L is equal to minus R to the what? 2L plus 1 times A sub L. The coefficients of the reciprocal and non-reciprocal powers in the solution are linked. Their fates are shared. But how do we figure out the coefficients? Substitution? I mean, the one thing we definitely don't want to do is, well, I mean, what other information do we have here? All we have is that the electric field is constant far away from the sphere, right? And so that gave us what? See, we have V of r theta is minus E naught r cosine theta for r much, much greater than r, right? But let's think about our solution. How does this solution work? When r is much, much greater than little r, these terms are negligible. And you just have those. Right? So if I think about, comparing star comparing with star, we find, well, you guys tell me, a sub, no, easier than that, a sub 1 r to the first power, right? P1 cos theta is equal to minus E naught r cos theta. I mean, that has to be the story, and a sub k, a sub l rather, a sub l equals to 0 for L not equal to 1, right? Because just the first order piece in here suffices to produce the far field effect. So from this, I can cipher that, in fact, and this is what? This is really just A1 r cos theta. So you guys, we can solve, what is A1? A1 is equal to what? Apparently minus E naught, right? And so that means A1 is this, and what's B1 equal to? Minus R to the what? What's
Plus 1.
2 plus 1 is 3, right?
2L plus 1. Oh, wait.
L is 1 here. L is 1. So 3, a sub 1. But that is minus r cubed, e sub naught. But there's a minus. That's minus e sub naught, right? So the minuses cancel, and I got that. Put it all together. My voltage is straight up. A1 is minus E naught R plus R cubed E naught divided by R squared, all times cosine theta. I did not understand this as an undergraduate when it was done. I did not know what we were doing. It was just dark magic to me. I just memorized enough of this stuff to make it through. But it's actually quite logical if you just follow the bits and pieces and just track. And you're willing to suspend disbelief on some math you don't know. Also, that helps. We can rewrite this formula a bit. This can be rewritten more nicely as what? Like E naught, or maybe minus E naught, times R plus big R cubed divided by little r squared times cosine theta, right? Hey, check it out. Now we can actually calculate this surface charge which is induced from a constant electric field. How would you find the surface charge? You guys remember how we did that? What was the deal? What was the surface charge? Remember the deal? Sigma, function of theta, it should be minus epsilon naught, partial v, partial r, isn't it? Is that right? That's the normal derivative to the surface, right? And it was minus the gradient, minus the normal derivative times epsilon naught was the surface charge density. Wasn't that one of our boundary conditions? And so, calculate. So we've got, epsilon naught, E sub naught, times 1 minus 2 big R cubed divided by little r cubed, I guess. But this is supposed to be done where? To be clear, this is supposed to be done at where? At the surface, right?
You might have missed the negative side.
Oh no.
When you took out the E naught.
Ah. Right there?
Yep.
Thank you. Why didn't I? Whatever. It's got to go somewhere. So that makes this a plus, right? And I still got that cosine theta out here. But we're again, this is happening at R, so what I really should say is sigma as a function of theta is epsilon naught E naught times what? 3? That's just a 3, right? When you plug in r equal to r, this gives us 3. 3 this times cosine theta. If I haven't made some stupid calculational mistake, that's the surface charge density. Let me see if that's what, I sure hope that's what Griffith says. Oh, good. This is equation 3.77. I can do math today. Hooray. Does this make sense? If we put theta, like going back to my original picture, what are the values of theta in that picture? You guys remember? Is it positive where it's supposed to be? Is it negative where it's supposed to be? Does it check? Theta equals to 0 up here. Theta equals to pi down here, right? So cosine's negative, cosine's positive. Yeah. And you've got like 0 charge in the 90 degrees, right? Pi over 2. Which makes sense because the electric field there is tangent. So the charge has to be 0 there. Otherwise it'd be moving. Anyway, so that's, I mean, come on, this example's cool. Like I like this example a lot. But the next one is even more exciting. Yeah.
I'm sorry, I must have just been distracted a little while ago. I missed how you got to the conclusion that A of L is 0 for all L does not equal 1.
Oh, because this is the boundary condition which is given to us.
Yeah.
So this is, we need this. But if you look at these, first of all, the B sub L terms, they're gone. And then we have A sub L times R to the power L times Legendre polynomials, right?
Yeah.
But this is a Legendre polynomial, cosine theta is. It's P1. And there's the R, which is supposed to be there too. So by process of like comparing, this must be the A1 term, and there is nothing else. Therefore, these are 0.
Okay.
That's using independence of the Legendre polynomials. All right, which we could prove, but then this would be a different class. What's that? Yeah, linear independence. Yeah. That is the independence I mean. I think they're more than that. They're actually like orthogonal in a certain sense, which is even better than just plain linear independence, obviously. But so the next and final example in this section, it's so this time he specifies a charge density. So up to this point, we've either specified the far voltage or the voltage on the sphere. But this example, we're specifying the charge density on the sphere. All right, so like, given sigma on sphere. All right. So he calls it sigma sub naught. So like sigma is equal to sigma naught of theta. It's a function of theta alone, all right? So again, it has the necessary azimuthal symmetry, right? No phi dependence. So it's tying together everything we've done today. It's very cool. So we want to find the voltage everywhere in this problem, inside and out. Inside, we need B0. for the inside part. Outside, we need the A 0. So you see, inside, we have the voltage at R theta is, the sum L equals 0 to infinity of A sub L R to the L Legendre polynomial cosine theta, right? Inside's that. Outside, we have the B sub L has to be the 1, because the A sub L's blow up at infinity, you see? So we're forced to write this if we want our potential to be finite. And we do. But what do we know about the potential? It's continuous. So these two guys have to meet right here. Right? And so that, because we have V in big R theta, has to be equal to V out R theta. All right? That forces these two things to be equal, replacing little r with big R. And by independence of the Legendre polynomials, I have that A sub L times r to the power L has to be equal, you see, to B sub L divided by r to the power L plus 1. So once again, we find a relation, an intertwangling, if you will. B sub L has to be equal to A sub L times r to the 2L plus 1. No minus this time. All right? So then, okay, that's great. How does the charge density come into play here? What am I using an eraser for? Like some sort of punk. A perfectly good eraser shirt here to use. Come on. So you guys tell me, how should I use the charge density? How does that inform the voltage? Well, we gotta wrap this up. What was it? Yeah, sigma is equal to minus epsilon naught partial v partial r, right? At r equals to r. And so, I know I'm out of time for today, but that's how you do it. You just, you do well, this isn't it either. It's not, that's not quite right. What was our boundary condition? Sigma over epsilon naught. What was it equal to? How did it go? Oh, maybe if I write it this way, sigma over epsilon naught r hat is equal to E out minus E in, right? Where I'm talking about the radial components. Remember the boundary condition? We had that the surface charge density was the difference of the outside and the inside normal component. But this is, if I haven't messed up a sign somewhere. So So this is his equation 3.82, if you look at it, is this. Again, we're out of time, but all you do is you differentiate these with respect to r. That gives you an infinite series for the out and for the in, right? And you can link them together because you know that these coefficients are together. And then that gets connected to the given sigma. And then you can solve for the coefficient, whichever one you keep, either the a's or the b's, using the purple trick and find the formula.
How is that non-trivial since at that point the out is being?
They're not, but no. This is this is E above, this is E below. The above is governed by this one. The below is governed by that one. They're different formulas.
And that r equals capital R.
They have to meet there. But the differentiation happens below and above.
Oh,
And then we join them at R. They're not equal. They're related by this charge density. But if you put this all together, then you can use the purple trick and solve for the coefficient that you want, that you keep.
so it's like a hinged derivative.
Yeah. And that's the last example in this section. So next up, we will do the multipole, and perhaps I will solve the mystery of the cylindrical coordinates. But anyway, thanks guys.